Welcome to solverfy.
We are asked to use Sollin's algorithm to produce a minimum spanning tree for weighted graphs. So in part A, we're given the weighted graph in figure 1 of this section. So for the first step of Sollin's algorithm, recall that we need to order all the vertices. So on the one hand, we have the rank that we're going to give the vertices. On the other hand, we have the descriptions of the vertices. So we have ranks 1, 2, 3, 4, and 5 for the 5 different cities in figure 1. And we'll assign to rank 1 the vertex San Francisco, to vertex 2, for rank 2 the vertex Chicago, to rank 3 the vertex New York, to rank 4 the vertex Denver, and to rank 5 the vertex Atlanta. And notice that there's really nothing special about this ranking. You could really rank these cities however you wanted as long as you only use each one exactly once. Now, for the next step in the algorithm, we want to choose the edge incident to each vertex with the smallest weight, or in the case of a tie, the edge that's first in the lexicographic order. So, consider our vertices again. So I'll write these in the same order as before. We have San Francisco, Chicago, New York, Denver, and Atlanta. And we have that for San Francisco, the edge incident to San Francisco with the smallest weight is the edge San Francisco-Denver. And then for Chicago, we have the edge incident to Chicago with the smallest weight is Chicago-Atlanta with the weight of 700. For New York, we have the edge incident to New York with the smallest weight is New York-Atlanta with a weight of 800. We have at the edge incident to Denver with the smallest weight is San Francisco-Denver again with a weight of 900. And finally, we have the edge incident to Atlanta with the smallest weight is Chicago-Atlanta again, which has a weight of 700. So we see that we only really are going to be adding 3 edges in this step. So first, I'll draw the vertices for this graph. So we have San Francisco, Denver, Chicago, Atlanta, and New York. and we want to add the edges, San Francisco to Denver. This is a weight of 900. The edge Chicago to Atlanta, which is a weight of 700. And Atlanta to New York, which is a weight of 800. In the next step, we want to determine the edge connecting San Francisco or Denver, so one of these trees, to one of the other three cities with the smallest weight, so to the other tree. So we find that the cheapest connection from San Francisco or Denver to one of the other three cities, Chicago, Atlanta, or New York, is from San Francisco to Chicago with a weight of 1200. So we'll add that edge to the graph. And now, since the graph is a connected graph now, the algorithm terminates, and it follows that by Sollin's algorithm, the resulting graph is a minimum spanning tree. In part B, we are given the graph in figure 3 of this section. And again, we're asked to apply Sollin's algorithm. So we'll want to use an ordering for the vertices. To make things simple, let's just choose an alphabetical ordering. So for example, A equals 1, B equals 2, and so on. And now, for the next step, on the left-hand side, I'm going to write all the vertices in their order. So A, B, C, D, E, F, G, and so on. And for the right column, I'll write the edges incident to each vertex with the smallest weight. Or, if we have a tie, the edge that comes first in lexicographic order. So for example, we see that the edge incident to A with the smallest weight is edge AB with a weight of 2. The edge incident to B with the smallest weight is the edge BF with a weight of 1. The edge incident to C with the smallest weight is the edge CD with a weight of 1. The edge incident to D with the smallest weight is again the edge CD with a weight of 1. The edge incident to E with the smallest weight is AE with a weight of 3. The edge incident to F with the smallest weight is BF with a weight of 1. The edge incident to G with the smallest weight is CG with a weight of 2. The edge incident to H with the smallest weight is HG with a weight of 3. The edge incident to I with the smallest weight is IJ with a weight of 3. The edge incident to J with the smallest weight is FJ with a weight of 2. The edge incident to K with the smallest weight is KL with a weight of 1. And likewise, the edge incident to L with the smallest weight is KL with a weight of 1. So for the next step, I'll draw a graph which has all the vertices of our given weighted graph, but no edges. So we're going to include the vertices A, B, C, D, and so on, all the way through L. And now I'll fill in the edges. So we have AB as an edge. We have BF as an edge. CD as an edge. EA as an edge. CG is an edge. HG is an edge. IJ is an edge. JF is an edge. And KL is an edge. These are all the edges that we found. Now notice that we still have 3 connected components in this graph. We want to make it a single connected graph. So for the next step in the algorithm, I want to connect the trees with vertices A, B, E, F, I, and J to one of the 2 other trees. So either the tree with vertices C, D, G, H, or the tree with vertices K and L. And we see that the weights of edges connecting the trees are always 3. So we need to choose the 2 edges that come first in the lexicographic order by Sollin's algorithm. So that means we must add the edge BC and we must add the edge GK. Now that we've added 11 edges, it follows that Sollin's algorithm terminates, and by Sollin's algorithm, it follows that the resulting graph is a minimum spanning tree.